Ever since we first looked up at the night sky, we've been explorers. It's just in our DNA. And that same curiosity, that same drive to figure out what's out there, has taken us from just staring at the stars to literally sending robots to other worlds. So today, we're going to journey through the basics of space exploration, and we'll start with the most fundamental question of all.
So what even is space? I mean, it seems like a simple question, right? But the answer, well, it really kind of depends on who you ask. If you're an atmospheric scientist, space is the place just beyond our sky. If you're an engineer, it's this incredibly harsh vacuum you have to build for. And if you're a theoretical physicist, well, it's the very fabric of space-time itself.
For a practical, nuts and bolts definition, we use something called the Kármán line. Just imagine you're in a rocket flying straight up. Once you hit about 100 kilometers or 62 miles, the air gets so incredibly thin that airplane wings just stop working. There's nothing to push against. And that's it. That's the line. It's the point where flying in our atmosphere, aeronautics, ends, and astronautics, the science of traveling in space, begins.
Okay, so before we blast off into the cosmos, we really need to understand our starting point. Earth isn't just some random rock floating around. It's a truly unique haven, a kind of protective bubble that makes all of this, well, all of us, possible.
Think about it. Our planet is in this perfect cosmic sweet spot. We call it the Goldilocks zone. It's not too close to the sun where all the water would boil away, and it's not so far that everything would freeze solid. It's just right. Just right for liquid water to exist, which is the key ingredient for life as we know it. Honestly, this is an unbelievably rare and privileged position to be in.
But our great location isn't the whole story. Deep, deep inside our planet, there's this incredible engine at work. We've got a liquid outer core made of churning, molten iron. And all that movement, this process we call the geodynamo, generates a massive planet-sized magnetic field. And that internal engine, the geodynamo, is absolutely crucial. The magnetic field it creates is basically an invisible force field wrapping all the way around our planet. And this shield is constantly doing battle for us, deflecting this non-stop stream of dangerous charged particles that are flying off the sun. Without it, life here just couldn't exist.
So we have this incredible planetary shield, but what exactly is it protecting us from? To answer that, we've got to look at the star at the center of it all, our powerful and sometimes pretty violent sun.
Yeah, the sun is not just a gentle, steady ball of light. It's a dynamic, churning ball of super hot plasma that is constantly blasting a stream of charged particles out in every direction. We call this constant stream the solar wind. But sometimes, the sun's activity gets way more intense. It has these sudden, violent outbursts. Think of solar flares as these giant explosions, releasing an incredible flash of energy. But coronal mass ejections, or CMEs, they're the real monsters. They can hurl billion-ton clouds of solar plasma and magnetic fields right out into space.
And this all leads to a really important distinction: Earth weather versus space weather. We all know about Earth weather, right? Rain, wind, snow. But space weather is totally different. It's driven by the sun's activity, and its impact is huge. A thunderstorm might make you cancel a picnic, sure. But a major space weather event, it can disrupt our satellites, mess with GPS, knock out entire power grids. It can threaten the very technology our modern world runs on.
All right, so we've got this dynamic, sometimes dangerous environment out there beyond our atmosphere. So the next logical question is, how in the world do we actually explore it? Well, it turns out there are two fundamental ways we go about observing the universe. Okay, the first way is called in situ. It's just Latin for in position. This is when we physically send something, a probe, a lander, a rover, to actually go touch and analyze an object directly, right there on site. The other method is called remote sensing. That's where we gather data from far away, without ever touching the object, by detecting messengers like light or radiation that travel from that object to us. And here's the best and simplest way to think about it. Your nose performs in situ observation. It has to be in direct contact with molecules in the air to smell something. Your eyes, though, they do remote sensing. They can see things all the way across the room because they're detecting the light that's traveling from those objects. It is the perfect analogy for how we explore space. So how do these big ideas turn into an actual flying mission? Well, every great mission starts not with a rocket, but with a question. A big, fundamental question like, was there ever life on Mars? From there, you pick a target, maybe a specific crater that looks promising. Then you have to figure out the how. Do you send an orbiter to map it from above, or a rover to get its wheels dirty and analyze the soil directly? You pick your instruments, you launch, and then the long, patient journey of discovery finally begins. All right, we've looked at our planet, we've looked at our star, and we've looked at the tools we use to get out there and explore. Now it's time to zoom all the way out and really consider our place in this grand cosmic story.
And this isn't just abstract stuff. This is a story about real human ingenuity. Just look at the journey of India's space exploration. It's incredible. From their first lunar mission, Chandrayaan-1, which actually discovered water on the moon, to Mangalyaan, which made India the very first nation to get to Mars on its first try, and of course, the recent successful landing of Chandrayaan-3 near the lunar South Pole. It's just an amazing testament to what we can do when we set our minds to it.
You know, all of this exploration, every probe we launch, every star we point a telescope at, it all ultimately leads us back to one of the most profound, most human questions we can possibly ask. Are we alone?
We've even tried to tackle this question with math. Now, the famous Drake equation isn't some magic calculator that spits out the number of aliens. It's not for finding an answer. It's a framework for thinking. It forces us to break down a huge question into smaller parts. How many stars are there? How many have planets? How many of those could support life? And so on. It helps us structure our guessing about one of the biggest unknowns there is.
And that brings us to the very end, to a final question I want to leave with you. As we keep sending a robotic eyes and noses out into the cosmos, what's the one discovery that you think would change everything? What is the one thing you really truly hope we find out there?